Hey, welcome back. Some of the most amazing shapes in the universe aren't just stuck in math books. They're actually hiding all around us, in plain sight, in some of the most powerful and elegant things you can imagine. Today, we're going to uncover one of them. All right, let's jump right in with a question for you. Take a look. A jet absolutely shattering the sound barrier, and a massive power plant cooling tower. They couldn't look more different, right? But believe it or not, they share a secret mathematical connection. So what's the connection? Any guesses? So first up, that jet. When it goes supersonic, it creates this cone-shaped shockwave that trails behind it. Now, where that cone of sound energy hits the flat ground, it doesn't trace a circle or a straight line. Nope. It makes this really specific wide-open curve. And then you've got the cooling tower. That shape, it's not just for looks. It's called a hyperboloid, and it's incredibly strong. It uses way less material than a simple cylinder would, and it's also perfect for promoting efficient airflow. The outline, that distinct curve you see, that's our mystery shape. And the answer that ties these two totally different things together, it's this beautiful geometric curve called the hyperbola. Both the sonic boom's pattern on the ground and the profile of that cooling tower are defined by this shape's unique rules. Okay, so what is a hyperbola, really? Let's dig into the secret rule that every single point on this shape has to follow. It's pretty cool. So here's the textbook definition. It's all the points where, if you measure their distance to two fixed points, we call those the foci, the difference between those two distances is always the same. And trust me, that word difference, that's the whole secret. This visual really helps it click. Just pick any point on either one of those curves. Now, measure its distance to each focus. If you subtract the smaller distance from the bigger one, guess what? You get the exact same number every single time. It's that constant difference that forces the points to create these two separate, perfectly mirrored branches. Okay, so a great way to understand this is to compare it to its famous cousin, the ellipse. With an ellipse, the sum of the distances to the foci is constant. That's what pulls it into a nice single closed loop. But for a hyperbola, it's the difference. And that's what makes it split into two branches that fly apart forever. So one's about the sum, the other is all about the difference. That's the game changer right there. All right, so now that we get the rule, let's break down the shape itself. It's kind of like looking at its anatomy, all the key parts that make it what it is. And wow, this diagram shows everything perfectly. You can clearly see the two branches of the curve. The foci are those two anchor points that define the whole thing. The vertices are the turning points on each branch. And see those dotted lines? Those are super important. They're called asymptotes. They're like guide rails that the curves get closer and closer to, but they never ever touch. So let's just quickly lock in those key terms, right? The foci are your two fixed points. The vertices are the turning points. The transverse axis is the line that connects those vertices, and the asymptotes are those boundary lines that the curve always approaches but never reaches. Okay, so we've got the shape, we've got the parts, but how do we describe this thing with math? Well, every single hyperbola can be captured in a surprisingly elegant and simple equation. Here are the two standard forms when the hyperbola is centered right at the origin. Look how similar they are. The only real difference is that minus sign. And here's the really important part, the thing to remember. Just look at which part is positive. Is it the x squared term or the y squared term? Because that one little detail tells you everything about which way it opens. And boom, this makes it so easy to see. On the left, the x squared term is positive, so the hyperbola opens out to the left and right. On the right, the y squared term is a positive one, so it opens up and down. That's it. That's the whole trick. All right, let's circle all the way back to the beginning. It's time to put all this theory into practice with that cooling tower and see how it all comes together. So we're revisiting the cooling tower. We know its basic shape is a hyperbola. But now we're going to use what we just learned to find the exact equation that describes that amazing curve based on its real-world design. So here's the blueprint, straight from the engineers. We have the key numbers. We know how tall it is, how wide it is at the very top, and its narrowest point right in the middle. These are the real-world clues we need to build our mathematical model. And when you take those real-world measurements and plug them into that standard equation we just looked at, you get this. This formula isn't just a bunch of numbers. That right there, that is the mathematical blueprint for a giant, real-world structure. How cool is that?
So you see, the hyperbola isn't just some abstract thing in a math class. It is a fundamental pattern baked into the universe and our own designs. It shows up in the path of a comet slingshotting around the sun, the shape of a guitar body, even in the pattern of light a lampshade casts on a wall. So my question to you is, now that you know what to look for, where are you going to see it next?